Good morning, everyone. So, we are continuing with our discussion about sequences of sets. So, let me start with another example. So, let an and bn be two sequences of sets. Okay. So, an and bn are two sequences of sets, and we want to check some of the properties related to lim sup and lim inf of unions and intersections of ans and bn. Okay. So, we want to examine the following four results. We want to examine first whether lim sup of an union bn is it same as lim sup of an union lim sup of bn. This is the first result that we want to examine. Secondly, lim sup of an intersection bn, can I say it is same as lim sup of an intersection lim sup of bn? Then can I say similar results are true for lim inf? So lim inf of an union bn, is it equal to lim inf of an union lim inf of bn? And the fourth one that we are interested in is whether lim inf of an intersection bn, is it equal to lim inf of an intersection lim inf of bn. So we want to check which of these four results are true. Okay. So we are going to use maybe some of the results that we derived yesterday, but mainly as hints. Okay, they would give you some hunch. So let me first write about LHS and RHS of first part. So let me start with the first one. So what I want is lim sup of an union bn. So this would be intersection union AK union BK, where K is greater than or equal to N is greater than or equal to 1. This is my definition of lim sup. Okay. So I want to check whether this is equal to lim sup of An union lim sup of Bn. So what is lim sup of An? It is intersection union AK, K greater than or equal to N greater than or equal to 1, union intersection union BK. So we want to check whether these two things are equal or not. Okay. So how to proceed? See, we want to check whether two sets are equal or not. So if I want to prove whether one set here is equal to another set here, ideally I should prove this is subset of this and this is subset of this. So let us try to see if we can get some of that. So let me start with some omega which belongs to LHS, that is omega belongs to lim sup of An union Bn. So this means omega belongs to intersection union AK union BK. Okay. What does this mean? This means omega belongs to union K greater than or equal to N AK union BK for every N. Okay. This is true for every N. Okay. So let me consider N equal to 1. So this means omega belongs to union k greater than or equal to 1 ak union bk. Okay. See, when I want to prove that, say, this thing, when I want to check whether this thing is equal to this, what I'm trying to do really? I'm trying to see if this intersection union thing is distributive over these two sets, over this union. Okay, so this intersection union thing, I'm trying to check whether it is distributive over this. Okay. Now, we know part of it already. What do we know? We know that union is distributive over union. We have proved this yesterday. Do you remember? So let us try to use that first. So what would it mean? So let me rewrite my LHS. So my LHS is intersection union AK union BK n greater than equal to 1 k greater than equal to n. So this I can write as intersection, and this inside part we have yesterday proved it is true, so it can be written as union AK union BK k greater than equal to n. Okay, this comes from not yesterday exactly, so this comes from the earlier result, that is union is distributive over union. We have seen this. Let me give some names to these, to make things easier. So let me call this as, say, Mn, this entire thing, and let me call this as Nn. So this becomes Mn union Nn. And in the same spirit, if I want to write RHS, how would it look like? My RHS is, okay, so intersection Mn union. So let me show you my RHS. So in my RHS, I have this as my Mn and this as my Nn. So it is intersection Mn union intersection Nn. So this was my LHS, and my RHS would be intersection Mn union intersection Nn. So ideally what I want to examine is whether intersection Mn union Nn n greater than or equal to 1, is it same as intersection Mn union intersection Nn. Okay, this I want to check. We have seen yesterday that this is not in general true. In fact, we came up with an example where this doesn't hold. But maybe here knowing Mn and Nn can help us a bit. So what do I know about Mn and Nn? So what I know is Mn is union k greater than or equal to n ak, right? So Mn is an union an plus 1 union an plus 2 and so on. Similarly, Mn plus 1 is union k greater than or equal to n plus 1 ak. So it is an plus 1 union an plus 2 and so on. So basically this part becomes Mn plus 1. So what I have is Mn is an union Mn plus 1. What does it mean? It means that Mn is superset of mn plus 1. Okay, therefore in general m1 is superset of m2 is superset of m3 and so on. Therefore mn is a decreasing sequence, decreasing, or you can say non-increasing if you want to be precise. Okay, are you with me so far? Now nn has been defined in exactly similar manner, just that instead of ans I have bns. Okay, so what I know is, in similarly I can prove that nn is also a non-increasing sequence. Okay, now does this help me? mn and nn being non-increasing, does it help me? Let me check. So let us start. What I want to prove is this. Okay, what I want to prove is this part. So now let me take omega from this LHS and try to check if it's in this RHS and so on. So consider omega belonging to intersection of mn union nn, n greater than or equal to 1. What does it mean? It means omega belongs to mn union nn for every n greater than or equal to 1, since it is in the intersection. So it means omega belongs to mn or omega belongs to nn for every n greater than or equal to 1. Okay. So what does it mean? It means that for every n, omega is either in mn or nn, even though mn's nns themselves are sequences. But what do I know about mn's and nn's are? They are decreasing. So let me try and draw a picture. Okay. So suppose this is my m1, then this is my m2, this is probably my m3 and so on, because they are decreasing. Okay, so what does it mean? It means that if suppose omega is in m3, so let us say omega is here, then it must be in m1 and m2 also. It can't happen that omega is in m3 but not in m1 m2. Okay, so what does it mean? It means that if omega is in mk for some k, then omega is in mn for every n less than or equal to that k. Let me repeat what I am trying to say. So since mn's are decreasing, we saw here that if omega is in m3, it has to be in m2 m1 also. That is exactly what I am trying to write over here. So if omega is in mk for some k, then omega has to be in all the mn's before that k because of the decreasing nature. And the same thing is true for nk's or nn's. Okay. So we are going to use this fact. So what I know is omega belongs to mn or omega belongs to nn for every n greater than or equal to 1. Okay. So consider n equal to 1. So there are three possibilities. Omega belongs to n1 but omega doesn't belong to n1. Okay. Then omega belongs to n1 but omega doesn't belong to m1, and omega belongs to both. Omega belong to neither is not a possibility because we already know this. Okay. So what happens here? If omega is not in n1, then it cannot be in n2 because of again this result. So if omega is not in m1, let's say, so it is somewhere here, then it cannot be in m2, m3 or anything. Okay. So in that case, so if omega is in m1 but not in n1, because of this what I know is omega cannot be in nk for any k, because once it is outside n1, n1 is the largest set, so it is outside everything. Okay, so this would force omega to be in mk for every k, because it has to be either in mk or in nk. So if it is not in nk, it must be in mk. Okay, so in this scenario omega belongs to mn for every n. Okay, this is exactly a dual of that. So in this scenario I would conclude omega belongs to nn for every n. Okay, and what about here? Here what I know is okay, it is in both. So then we will check for second one. So does omega belong to m2 or omega belong to n2? Again there are three possibilities. One is similar to this, one is similar to this, and the third one is here. So exactly similar three possibilities. So this will continue till some k. So maybe you have in both. So finally I have two possibilities. Omega belongs to mk and omega belongs to nk for every k, or you find a k at which this exercise stops, so at which omega belongs to only one of mk and nk, and after that point onwards, just like these two cases, omega will belong in only one of them. Okay, so omega will belong to intersection. Okay, let me write just omega will belong to m n for every n greater than equal to k, or omega will belong to nn for every n greater than equal to k. One of these things will happen. Okay, so what does this mean? This means that in every case omega is either in intersection mn for every n greater than equal to 1, or omega is in intersection nn for every n greater than equal to 1. Getting my point? Let us check once more. See, here I have omega is in mn for every n, so I am done. This is also fine. And here initially it is in both mi's and ni's, and after a certain point either it is throughout in both, in that case it is in intersection of mn's as well as intersection of nn's, or after a certain point it's either in mn's or in nn's, but in any case, so if it's in mn's, then combining this with the earlier thing that up to k it was in both, I get it is in total intersection. Okay, so what does it mean? This means that omega belongs to intersection mn union intersection nn. Okay, and this is exactly the RHS that we were looking for. So what I have so far is intersection of mn union nn is subset of intersection Mn union with intersection Nn. Okay, so one part of the proof is over. Okay, remember we have used the fact that Mn's and Nn's are decreasing. Without that, this proof wouldn't have gone through. Okay, now to prove equality, I need to say that right hand side is also subset of left hand side. So let us check if that is correct. So now consider omega belonging to intersection Mn union intersection Nn. Okay, so what does it mean? It means omega belongs to intersection Mn or omega belongs to intersection Nn. So this part means omega belongs to Mn for every n or omega belongs to Nn for every n. Of course, there is a third possibility that it is in both Mn and Nn, but right now let's not worry about that. So what does this mean? This means that omega belongs to Mn union Nn for every n, and hence omega belongs to intersection of Mn union Nn for every n. So this part is actually routine. Here I don't need non-increasing nature or anything. Okay, so from here I can easily conclude that RHS is subset of LHS. So we have finally proved what we wanted to prove. So what we have proved? We have actually proved lim sup of An union Bn is equal to lim sup of An union lim sup of Bn. Okay, this is my final result. I know here we haven't proved that, but this was a sub part and our other part was already done. Okay, I have one result, so at least the first part is true. Now let us try to use the results that we have proved about complements of sets. Okay, so what I know is from this, if suppose I had sequences An complement and Bn complement, the result is going to be true for them also. Okay, so I can write lim sup of An complement union Bn complement is equal to okay, one result is true. So can we use this for some next things? Okay, now I know this, so if I take complements on both the sides, what do I get? I will get lim sup of An union Bn whole complement is equal to lim sup of An union lim sup of Bn and again whole complement. Okay, so if I use De Morgan's law and the results about lim sup lim that we have proved, we know lim sup of some complement of lim sup, it would be lim inf of An union Bn whole complement, and this side would be lim sup of An whole complement intersected with lim sup of Bn whole complement. This is just De Morgan's law, nothing else. Okay. No, De Morgan's law. Yeah, only De Morgan's law so far. And here I have used properties of lim sup lim inf. Okay. So the left hand side becomes lim inf of An union Bn whole complement by De Morgan's law is An complement intersection Bn complement. Okay, and this would become lim inf of An complement intersection with lim inf of Bn complement. So what we have is lim inf of An complement intersection Bn complement is equal to lim inf of An complement intersection with lim inf of Bn complement. And now, right now we have the result for complements, but we can rewrite it in terms of original sets. Okay, so how would we do that? We would say that this result is true for complements also. So let me start with that. So whatever I did just now, this part is kind of like reverse thinking. Okay, so let me start with the actual proof for part 4, I think. Let me check. I think it is part 4 of my original statement. Yeah, part 4. Okay, so now I want to prove part 4 and I will use part 1 for it. So using part 1 for An complements and Bn complements instead of original sets, what do I get? I get lim sup of An complement union Bn complement is equal to lim sup of An complement union lim sup of Bn complement. And now you take complements on both the sides. So taking complements on both the sides, what do I get? I get, by the way, spelling of complement is E, not I. I is you're wishing someone. So An complement union Bn complement whole complement is lim sup of An complement union lim inf of Bn complement and whole complement. Okay, so this is same as, again we'll use properties of lim sup lim inf and De Morgan's law. So this becomes lim inf of An complement union Bn complement whole complement equal to lim sup of An complement whole complement intersection with lim sup of Bn complement whole complement. So this is lim inf of something complement is lim inf of An intersection Bn. Okay, De Morgan's law again. And this is lim inf An intersection with lim inf Bn. Okay, so therefore we have actually proved that fourth part is also true. So first and fourth are true. What about second and third? Okay, so let me try to see if we can do something about second. Okay, so I want to examine 2, means I want to examine whether lim sup of An intersection Bn is it same as lim sup of an intersected with lim sup of Bn. Okay. So lim sup of an intersection Bn, that is the LHS, would look like intersection union AK intersection BK, K greater than or equal to N, N greater than or equal to 1, and lim sup of An intersection lim sup of Bn would be intersection union AK intersected with intersection union BK. So if at all this is going to be true, then we are kind of claiming that this union is distributive over intersection. But we have seen in the earlier lecture that this is not the case. So maybe this is wrong. So let us try with some counter example. Okay. So the earlier example might also work. So that's a homework. Check whether the earlier example works for this case, whatever we did in the earlier lecture. But let us try a new example here. So let me define An as 1, 2, 3 up to n if n is even. Okay, and let me define it as just singleton n if n is odd. And Bn, let me define in the reverse way. So Bn is singleton n if n is even, and Bn is 1, 2, 3 up to n if n is odd. Okay, just write down what is A1, A2, B1, B2, and it will be more clear. So we will first try to compute An intersection Bn, then we'll take its lim sup, and then similarly we'll try to compute these and check if they are unequal. Now first, An intersection Bn. So An intersection Bn. So when n is odd, I am getting An equal to n and Bn equal to 1 to up to n. So the intersection is just singleton n, and in fact it is the same even when n is even. So intersection is singleton n for every n. Okay. So if I now want lim sup of this intersection, so lim sup of this intersection is going to be intersection union AK intersection BK, K greater than or equal to n, n greater than or equal to 1. And we know this is singleton K. So singleton K, if you take union over all K greater than or equal to n, it is going to be n, n plus 1 and so on. But then intersection is going to be an empty set. Okay, because the first set is 1, 2, 3 and so on. Second set is 2, 3, 4 and so on. So at the end, nothing remains. In fact, this can be seen from the other definition of lim sup also. Lim sup contains those terms which occur infinitely often. Here every set is having a distinct element, so no element occurs infinitely many times. So lim sup is empty. And what about lim sup An and lim sup Bn? Let me try that. So because An is 1, 2, 3 up to n for even n and singleton n for odd n, what can I say about lim sup n? So lim sup n is intersection union ak, k greater than or equal to n, n greater than or equal to 1. So let me try. Intersection n greater than or equal to 1, union k greater than or equal to 1, n ak. Okay, now there are two possibilities. Let me start with n is even. So if n is even, union k greater than or equal to n ak would be, for even n, my n is 1 to up to n. Okay, so this would be 1, 2, 3 up to n. Then next set is, so this is my an. My an plus 1 is just n plus 1. Then an plus 2 is 1, 2, 3 up to n plus 2. Then an plus 3 would be just n plus 3, and so on. Okay, so the union has to be the largest set, so it would actually be 1 to up to everything. So this would be entire set of natural numbers. Okay, and hence lim sup n would be intersection over set of natural numbers. So it is just set of natural numbers, because for every n, okay, I wrote down for even n, but even if you consider odd n, you are going to get exactly same thing. So for every n you get set of natural numbers, and hence your lim sup turns out to be this. Okay, now there is some homework for you. So homework is, check what happens to check what happens to lim sup bn. You would get lim sup bn also to be n. Okay, and as a result, lim sup of n intersected with lim sup of bn is actually n, whereas my LHS is just an empty set. Okay, so what we conclude is lim sup of n intersection bn is not same as lim sup of n intersected with lim sup of bn. Okay, so result 2 is not true. Now can we use this to say something about 3? So if result 3 were true, then by complements we could probably get result 2 also, but that is not happening. So 3 also must be false. So homework is, use this or some other example to show that the result in 3 also doesn't hold. To show that 3 doesn't hold. Okay. Okay. So we have proved some properties of lim sup lim. Now we have to do couple more things. So if someone now tells me that an converges to a and bn converges to b, from this can I conclude something about an union bn or an intersection bn? Okay, so if an is a sequence, bn is a sequence, then an union bn is another sequence, an intersection bn is another sequence. So what can we say about those? So let us try to examine. So what is given to me is an converges to a and bn converges to b. What does it mean? It means that lim sup an is equal to liminf an is equal to a, and lim sup bn is equal to liminf bn is equal to b. Okay, so let us first try for an union bn. Okay, consider liminf of an union bn. So by definition this will be union over intersection ak union bk, k greater than or equal to n greater than or equal to 1. Okay, so what does it mean? So if omega belongs to liminf of an union bn, then it implies omega belongs to intersection k greater than or equal to n ak union bk for some n, say n naught. This means omega belongs to intersection k greater than or equal to n naught ak union bk. Okay, this came because we are considering union. Okay, so what does this mean? This means omega belongs to ak union bk for every k greater than or equal to n naught. So this implies omega belongs to ak or omega belongs to bk for every k greater than or equal to n naught. Now, what does this mean? This means that omega belongs to ak union bk for all but finitely many k's. Okay, omega belongs to ak union bk for all but finitely many k's. Okay, because except for, okay, so omega is in ak union bk for all but finitely many k. So there are three possibilities. Omega is in ak for all but finitely many k, second possibility is omega is in bk for all but finitely many k's. Of course, both these include the possibility that omega is in both for all but finitely many k. Okay, and the third possibility is omega is in ak infinitely often and omega is in bk infinitely often, but it is not in any one of these for all but finitely many. What do I mean? Maybe something like, say, omega is in ak for every odd k and omega is in bk for every even k. So in that case, what would happen is omega is in ak infinitely often, omega is in bk infinitely often, but I cannot say that omega is in ak for all but finitely many k, and I cannot say that omega is in bk for all but finitely many k. Okay, so in this case, if this happens, then omega belongs to liminf of ak, because that is definition of liminf. In this case, it will be in liminf of bk, and in this case it will be in lim sup of ak and lim sup of bk. Okay, so omega is in lim sup ak, liminf ak is same as lim sup ak, so omega is in liminf ak, here omega is in liminf bk, or here I am saying omega is in lim sup and liminf are same, so liminf ak and liminf bk. So what we are concluding is omega is in lim_inf of AK union lim_inf of BK. Does that help me? So what we have proved so far is lim_inf of An union Bn is subset of lim_inf of An union lim_inf of Bn. Okay. But in this case, what we know is lim_inf of An and lim_inf of Bn are existing. Actually, they are same as limits. So what I know is this: lim_inf of An union Bn is subset of A union B. Okay. Now let me try for lim_sup. So we have proved this: lim_inf of An union Bn is subset of A union B. If I want to prove reverse way, so if omega is in A union B, what does it mean? It means omega is in A or omega is in B. If omega is in A, then it means omega is in lim_inf of A, and here it means omega is in lim_inf of B. So similarly, I can say omega is in lim_sup of A or omega is in lim_sup of B. Okay. What does it mean? This means that omega belongs to An for all but finitely many n's, or omega belongs to Bn for all but finitely many n's. Okay. As a result, omega belongs to An union Bn for all but finitely many n's. Therefore, omega belongs to lim_inf of An union Bn. Thus, we have proved that A union B is subset of lim_inf of An union Bn. Hence, what I have is lim_inf of An union Bn is same as A union B. Similarly, I can say that lim_inf of An complement union Bn complement is same as A complement union B complement. Okay. And if I take complements on both the sides, I will get lim_sup of An intersection Bn is same as A intersection B. Okay. So what we have got is lim_inf of An union Bn is same as A union B. Lim_sup of An intersection Bn is same as A intersection B. But we want to prove that limit of An union Bn is A union B. So what can I do about lim_sup of An union Bn? So consider lim_sup of An union Bn. So this is, so consider omega belongs to this set. So this implies omega belongs to An union Bn infinitely often. So there are three possibilities again. Omega belongs to An infinitely often, or omega belongs to Bn infinitely often, or omega belongs to both infinitely any of one. Okay. In fact, if ideally I can say omega belongs to an for all but finitely many n's. Similarly, I can say omega belongs to Bn for all but finitely many n's. Or omega belongs to An infinitely often and omega belongs to Bn infinitely often. So this would mean omega belongs to lim sup of An, which is also equal to lim inf of An, and omega belongs to here lim sup of Bn, or omega belongs to both. So lim sup An intersected with lim sup Bn. Okay. So what does it mean? It means that omega is in lim sup An union lim sup Bn, or you can say lim inf also. So this means omega belongs to A union B. Therefore, what we have concluded is lim sup of An union Bn is subset of A union B. But we also know that A union B is nothing but lim inf of An union Bn. We have already proved that. And we know that lim inf is always subset of lim sup. So now everything has to be equal. Okay. So we have proved that lim inf of An union Bn is same as lim sup of An union Bn, and it is same as A union B. Okay. Homework is try the similar result for A intersection B or An intersection Bn. In fact, we have done half of the proof just during this proof. Okay. I will stop here.